Hello again, Dr. West here. This is part 2 of our discussion about chapter 12, which is about motivated behaviors and emotion. So what we talked about in part 1 was sort of the overall idea of what is an emotion exactly and how does that relate to motivated behaviors. And we sort of talked about that. And then I brought in the final 2 sensory systems that we didn't discuss previously when we were really going over the sensory systems. And I said that I had done that on purpose because, particularly with these 2 sensory systems, they were actually responsible or could be responsible for producing motivated behavior, which we'll actually get to in the third part of this particular unit, of this particular chapter. So in the next video after this one, because we're going to talk about how sight and smell of food leads to feeding behavior. Right? And I had you imagine your favorite food, that sort of thing. Well, if you felt hungry after that experience, that was normal. That's how your brain should be responding, right? Because again, thinking about food or even remembering favorite foods, talking about foods can trigger it. But especially if you actually see the food or smell the food, it's going to trigger you to want to do a motivated behavior. But we also talked about how, especially the sense of smell, kind of cheats, and it doesn't follow that standard pattern completely, that it bypasses the thalamus and actually goes to some other brain regions, including the amygdala first. So there's a heavy emotional component associated particularly with smell and how smells can trigger certain emotions. So what we're going to do in this particular lecture is sort of bridge some of the gaps there. We're going to talk about a few more themes sort of related to this. And the first thing that I'm going to do is start off by discussing some evolutionary influences on behavior. So I'm going to talk about how this was important for our ancient ancestors. And one of the first things that I'm going to talk about are what are called innate releasing mechanisms. And a lot of different organisms have them. Basically, they're these hypothetical mechanisms that detect certain kinds of sensory information or sensory stimuli in the world, and then it produces an action in the organism. So I'll give you one in cats, and I'll give you one in people. Actually, I'll give you a couple in people. But for example, you don't have to teach these behaviors. That's why they're called innate. And then the releasing mechanism part means that once the innate part is triggered, right, once the stimuli is there and it triggers, right, it's going to release this whole sequence of behaviors that the organism is going to do that it hasn't had to learn. So, for example, in cats, right, you don't have to teach a cat to try to attack something. Right, you can wiggle a string, you can do a little toy mouse, you can even put it outside and let it chase real mice, right? Cats do not actually have to learn to chase things. Now, they might have to learn how to get better at it or certain strategies from watching other cats, right? But if you take a cat that's been newly born, that's never had a chance to actually watch another cat do this, they will still be able to do it because it's somehow built in to just who they are. And if they see something moving and you can wiggle your finger, or you can wiggle a string or anything that you want, that's going to trigger that releasing mechanism, and the cat's going to lunge at it and try to attack it. Right? So that's what we mean by these innate releasing mechanisms. Now, again, most of them are designed to be evolutionarily beneficial. And what I mean by that is that it helps keep the species alive, helps keep you alive. So, for example, one that a lot of people have, right, is being afraid of snakes, even if you've never touched one, right, or being afraid of other types of creatures. Mine, I told you before, was spiders, right? I haven't, unfortunately, at this point, touched spiders, but it wasn't on purpose, I can guarantee you. But I've actually never had a legitimately bad experience with spiders. As I said, I had one get on me a couple times, and that was, of course, totally freaky and scared me to death. But nothing bad actually happened. I didn't get bit. I didn't get any kind of infection. Nothing actually happened, yet I still responded as if I was about to die, right? And that's sort of why we think it was a good idea, is because back in the day, there are some snakes, and there are some spiders, and there are some other situations where, again, if you had gotten bit, it could have been deadly. And so it made sense that our ancient ancestors would have been afraid, and those that had that releasing mechanism to respond with fear and to try to get away from it would have been healthier than those that were like, oh, I'm not going to worry about it, and then might have happened to get bit by one that was dangerous. So it makes sense that we have some of these releasing mechanisms. So again, our brains have built into them all kinds of sets of these patterns or norms that, again, once the stimulus is there, triggers these responses. And we think that even though a lot of this may have some cultural influence to it at this point, there are some things that just don't. There are some things that just happen regardless of a person's culture, that they are just built in because you are just human. A couple of them are facial expressions. And some of the neat evidence for that is that individuals that are born blind, so they're never actually able to see another person give a facial expression, are still able to produce them. So there's got to be something that's built in that causes that to happen. And even some other things like mating behaviors, sex, making out, all of those may also be initiated by those innate releasing mechanisms. So we know that there's a lot of things that happen thanks to our ancient ancestors that got passed on genetically that we now do that influence our behaviors. Again, we know that there are some neural circuits that exist that help keep us doing things that are good for us. Right? We call these reinforcing behaviors, or behaviors that are reinforced. Reinforced is another way of a fancy way of saying rewarded or encouraged. Right? If you hopefully you remember from Introduction to Psychology, a reinforcer in operant conditioning was something that makes the behavior happen more often, or an event that strengthens the behavior that follows it. So if you wanted your dog to sit, and you said sit, and the dog did, and you gave it a treat, you were giving the dog a positive reinforcer. Right? What we know is that it's not just that I got a treat, or it's not just that I got something good, or I got a reinforcer, is that the brain actually responds when you've been presented with a reinforcer. And that experience of pairing a behavior or a stimulus with a reinforcer, right, changes the way your brain communicates with itself. So what we know is that complex behaviors can be learned, and that it's not a new thing. Our ancient ancestors were able to do this, and because it worked so well, it's been kept, and now we still do it today. So what we also know is that the environment that you are in is going to heavily influence the types of behavior that you do, because your environment, either on purpose, like a parent purposefully giving a child something for doing something good, is going to influence you, or your environment is going to indirectly influence you. Right? So we also know the environment has a big role to play on our behavior, but it's not just the environment does it. It's when the environment influences us and we have this experience of a reinforcer, it also goes in and it changes the way our brain communicates with itself. So it's kind of a circle pattern, right? This is why we never say it's all nature or it's all nurture. And actually it's neither, it's both, but it's also neither, because when the two start interacting with each other, you sort of get this third middle component of you get growth and you get brain structural changes that encourage growth in between. So here are some other examples of environmental influences on behavior. And again, some of them are on purpose and then some of them aren't necessarily on purpose. For example, this first one, not on purpose, at least hopefully not. The first one is called a learned taste aversion, and I'm sure most of you probably have one. So think about the last time you had food poisoning, right? Or you got really sick after eating a certain kind of food. Most people say if that's ever happened to them, like they don't ever want to eat that food again, or at least it's going to be a really long time before they want to eat that food again, right? And if you think about it, this is one of those great blends between evolutionary, right, something our ancestors did, and the actual environmental influences. Because way back in the day, right, if our ancient ancestors ate something and it made them really sick and they were lucky enough to have not died, it would have been really smart for them to go, you know what, that thing made me sick. I'm not going to eat that again. I don't ever want to eat that again, right? But we still do it today, right? Even if it wasn't actually the food that made us sick, even if we just happened to eat something and then got a stomach virus, it was actually a virus that made us sick and it wasn't the food that was bad, right? We still put that link together in our head. We still say, hold up, I was eating, I don't know, I'm going to name a random food, and I'm going to use this example because it really did happen to my cousin. He was eating chili, right? Ended up getting a virus. It was nothing wrong with the chili because no one else actually got sick, right? But now, like, he doesn't even want to think about chili, nonetheless smell it or see it, right? Because it makes him think about that time where he ate it and then got sick. So he quickly learned, right, that stuff makes me sick. Again, even though he knows logically that it's not true and that it was a virus that he had, it doesn't matter. The brain changed and quickly made that association between that stuff is poison, don't ever eat it again. Make sense? Okay. Some other things that our brains can do is we can be prepared for stuff. We can have a predisposition to respond to certain stimuli differently than other stimuli. Your brain is kind of pre-wired to make certain kinds of associations than not others. You're wired to make associations between the way that food smells and health. So if food just smells weird to you, it probably means something's not good about that food. That food is probably old or spoiled. And again, that's probably good, right? Because it will help you avoiding eating something that could potentially be poisonous or could potentially make you sick. All right, so it's a good thing that we have some of these things sort of kind of built in. So let's jump into what is actually happening in the brain. Let's talk about some of the brain structures that are sort of responding when some of these things are happening. Hopefully, a lot of these brain regions are going to sound familiar because we technically talked about them already, but here's where they're going to come in and be important. Together, a lot of these structures, all right, are going to be associated with this one big one here called the limbic system. So the hypothalamus was part of the limbic system. And then the other structures that were in the limbic system, including the hippocampus for remembering stuff, the amygdala, we talked about that in those two in the first unit, right? The amygdala for processing emotion, all of those were part of the limbic system. And so it makes sense that some of these kinds of structures would be part of our motivated behavior. So the job of the hypothalamus was to be gathering information from the body about whether or not we were in a sense of homeostasis, whether or not we had the right level of things in our body that we needed. And if we didn't, right, as you learn from the end of Unit 2 especially, it's going to send out some messages using the pituitary gland and the endocrine system to fix it. Right, so if your blood sugar is too high, the hypothalamus is going to let the pituitary gland know, and the pituitary gland is going to let the rest of the body know to hopefully release some insulin and bring the blood sugar level back down. Right? So that's a good thing that we have going on. Again, with the rest of the limbic system, you have the hippocampus, so you can remember where good things are and you can remember where scary bad things are. You also have the amygdala so that you can associate an emotion with it. So you can associate happiness with good things. You can associate scariness with bad things, right? So, and then you have the frontal lobe there so that you can actually make good choices of, wait a minute, when I went that way, that's when I went by the house with the scary dog. So maybe I'll go home and walk this way so that I don't have to go by the scary dog. So again, all of these brain regions can sort of work together. Plus they have the benefit of being able to send out messages via the endocrine system to keep your body in balance. And again, we called that homeostasis. So all of this sort of motivated behavior is also sort of being prompted, underlying underneath, by a need for our body to keep itself in homeostasis. In other words, keeping our critical body functions within this sort of narrow, fixed range that keeps things functioning properly. So again, what else is going on related to this homeostasis? Well, again, you've got that endocrine system and nervous system constantly communicating with each other. Right, so you've got all those feedback loops that Dr. Bennett was talking about, right? So the endocrine system is sending messages to the nervous system. If the nervous system decides it's good, it will send a message saying, all right, endocrine system, you can stop now, Or if the endocrine system sends a message and the nervous system realizes something's off, it says, endocrine system, you need to restart that, please, or release more of that, please. All right. We also have regulation within the nervous system. So you have brain regions themselves that are influencing each other, as well as being influenced by hormone release. And then, as I said before, experiences themselves alter the structure and function of your brain, especially the hypothalamus itself, as well as some of our memory and reward areas that you're going to hear more about. So again, it's really important, not just that our body can respond, but that our body can then change and remember how it responded so that it does it better later. So again, what are some of the things that we really need our body to be able to do? Well, again, we need our body to be able to help us do certain things to keep us alive, right? And what's really happening in the brain isn't going to seem really that different from a lot of other stuff, right? You're still just going to have electrical stimulation of different parts of the hypothalamus, but ultimately what will happen outwardly are very different goal-directed behaviors. And that's what's really cool to me, right? Is that depending on exactly where you stimulate the hypothalamus is going to depend on exactly what's released, and then that will exhibit exactly what happens as far as the behavior goes. So it might trigger eating and drinking behavior. In some animals, it might trigger digging behavior. It might trigger a displaying of fear behavior. And my favorite example of that is like the cat that you usually see at like Halloween, right? Where it's got all of its hair standing up on end, it's got its back arched or whatever, right? Like that's that fear posturing display. It might initiate predatory or attack behavior. It might initiate reproductive type behaviors, right? Flirting behaviors, sexy type behaviors. So again, depending on what gets stimulated, it's going to produce a behavioral change in you that you then actually demonstrate. So here is really where we see the title of this class coming to be. The brain is producing behavior. So brain and behavior. But again, the ultimate goal of these behaviors is to make sure your body is getting what it needs to be able to survive, or to do what it needs to do to be able to survive, not just in the moment if something is scary, like the fear and the attack behaviors, but also long-term, as well as species long-term with some of the reproductive behaviors. And again, it comes down to a lot of that limbic system that we talked about. So you're going to want to make sure you have reviewed the limbic circuit. You're going to want to make sure you have looked back quickly at the cingulate gyrus. You're going to want to make sure you've looked back at the hippocampus and what it's doing. Technically, there is a formal hippocampus as well as something called the parahippocampal cortex. I want you to focus mostly on the hippocampus itself. It's a distinctive three-layered subcortical structure. Again, its main role is to help with certain kinds of memory and spatial navigation. So it helps you remember certain kinds of things and then where those certain kinds of things were. Right? So if you think about it from a food perspective, the hippocampus helps you to remember, wait a minute, I think I remember seeing a cheeseburger in the refrigerator or whatever it was. All right. So again, you remember when it was, what it was, and sort of where it was. And you need that hippocampus as part of the limbic circuitry. Again, here to sort of in picture form, it sort of makes kind of like a loop. All right. It also includes the amygdala. This is where you're getting information about that emotional component. Right. So if there's ever something, again, scary, or in this case, happy, hopefully food makes you happy. Right? The hippocampus part, helping you to remember where it was. And again, the hypothalamus also bringing in all the information from the limbic system, as well as sending information back out to, not the limbic system, excuse me, the endocrine system, should there need to be changes made with the hormone production in the body. So that being said, let's quickly review the amygdala. The amygdala is the emotional processing region of the brain. Again, you've got one on each side, and it plays a role in emotional and species-specific behaviors. So there are some things that other animals will do because of their amygdala that you won't necessarily do, and that's totally and absolutely fine. But in you as a human, your amygdala is going to help you do emotional processing behaviors and species specific behaviors. And it's receiving input from all of your different sensory systems. It's what we call multimodal. It's receiving and responding to more than one sensory modality. But if you remember, most of those sensory systems have been filtered except for that sense of smell. And your amygdala is highly involved in your arousal response and the processing of fear-relevant stimuli. And that's really good because, again, if something is super scary, it probably also means it's dangerous. And you want to be able to get yourself aroused, that fight or flight thing, by doing two things. One, remembering what was scary so you hopefully don't encounter it again. But even more critical for this exact moment is sending that message to the hippocampus so it can send it to the pituitary gland, so it can send it to the adrenal gland. You can have that nice HPA response that you learned about in the last unit, and you can have that fight or flight response if you need it. Right? So everything is sort of coming together and functioning here. All right, so that's sort of the underlying sort of brain mechanism of what's going on. Now I want to move one more kind of step forward and talk a little bit more about emotions themselves, right? So how do we actually produce an emotion, and can we actually control our emotions? And I'm going to start off a little bit with some silliness here, but can we actually control our emotions? And the answer is sort of. We can sort of control our emotion. Mostly what we can really control, though, is sort of like the expression, and even some of us aren't so good at that. I always joke, the first one here is kind of me. Controlling my tongue or my mouth, what I say is not so much the problem, it's my facial expressions that need work. Yeah, I'm definitely guilty of that. I have a really hard time not showing what I'm feeling on my face, especially when I'm sitting in a really boring faculty meeting and they're talking about stuff that should have been in an email. But nonetheless, again, the idea of an emotion, remember, is it was a coordinated series of behaviors, right? So it wasn't just stuff that was happening on the inside, it was also a series of stuff happening on the outside, and facial expressions is one of them. I just absolutely love this one. The boss telling you to dress for the job that you want, not the job that you have. And now you're sitting in a disciplinary meeting wearing a Batman costume. Yeah, didn't control my emotions very well there. And then I also love this image of the different kinds of cat emotions. And if you are a cat fan at all, or even if you're not a cat fan at all, you might still find this funny. But here's how a cat looks when they're mad and irritated and sleepy and dead and alive and content, and hopefully you get the point of the joke there. But all right, realistically, how do we control our emotions? Can we? And again, the answer is sort of, and it comes down to something called executive control. Now, executive control, and I'm going to skip ahead here just a minute, is done by the frontal lobe. Right, the various parts of the frontal lobe. So we talked about this a little bit when we were talking about motor movement, right? You needed that executive functioning of the motor cortex and the premotor cortex to decide that you wanted to make movements. But now we're talking about other kinds of decisions, or deciding about our emotions, deciding to control our emotions. So we're going to talk about some of these other parts of the frontal lobe here. So again, I just wanted to sort of let you have like a visual in your head as we go through it. But talking about controlling our emotions, we need to talk executive control. So executive control processes live or reside in the prefrontal cortex. This is where you have your highest order cognitive control. Right? This is where the things that make us the most uniquely human live, is right there in our frontal lobe. This is also one of the last brain regions that's going to be myelinated and connected to the rest of our brain. It's one of the last one that gets finished. So you are usually a late teenager, early 20-year-old before this is actually done. So it makes sense that younger children are going to have a lot harder time controlling their emotions than adults would. And you can also tell the adults that have not practiced and have not finished, right, with working with their executive control, because they don't do very good at it either. But that's a whole different lesson for a different day. hopefully, let's assume they were able to get their neurons and everything myelinated when, they were supposed to. What we do know is that this is how it should work. Your higher order cognitive control includes being able to plan out actions and execute them in order to accomplish goals. Well, there's a lot to that statement. That means, first of all, that you had to think about a goal that you wanted, right? Then plan how you wanted to get there, and then actually do the plan. That's three really kind of complicated things, right? And I'm going to kind of confess on myself here for just a minute. ADD runs in my family. And this is one of the things that's challenging to someone with ADD, right? Is doing all of these things. I have no problem setting goals. I don't usually have a problem acting on the goals. What I tend to have a problem on is the third part, which is actually executing on the actions. And what I have found works for me, right, is breaking it up into tinier and tinier and tinier pieces. If I give myself too big of an action, it's harder for me to execute. So it's not like my frontal lobe doesn't work, it just works differently, right? And that's what I want people to understand, is that's how we actually have to train ourselves, is that we have to understand how our frontal lobe works, right? If you're struggling with some of this, there could be multiple reasons why it's happening. It could be because you made a goal that was just not accomplishable no matter what, right? It could be because you planned actions that weren't possible no matter what. Or it could be because you made some kind of, you tried to do some kind of execution that you're just not able to do. Sometimes there are fixes. Sometimes you can change the goal to something more realistic. If that wasn't the issue, sometimes you can change the specific actions. Or you can do like I do and break them up into different categories or different chunks of action, right? And you can change your method of execution. So again, there's different things that you can do there. The other thing that our higher order cognitive control does is helps us to maintain and sequence information. This is always why, and again, maybe this is just why my teaching style is different from everybody else's. I like to sort of go back and forth between big picture and little information, because that's how I maintain the sequence of information. I'm like, okay, here's what I'm working towards, the big picture. Now I'm going to look at this little piece and this little piece. All right, let me go back to the big picture and make sure I got it. Okay, I got it. Right? And again, that's how my frontal lobe helps me organize all that. So all that executive control is housed in the prefrontal cortex. And let me go back to the picture here. That prefrontal cortex is the tippy part here of the brain. Right? It is also able to decrease the response of the amygdala. So it can actually decrease the amygdala's emotional responsiveness. So, much like a composer, so if you think of like a music composer standing up in front of a big group of musicians, right? That composer will select the best actions for the current time, place, and context. They may tell one group of musicians to play a little louder, one group to play a little quieter, one group needs to stop right now, another group needs to start right now, right? Or even somebody that's not working with live musicians and someone that's just using a big mixing board. That's kind of what your prefrontal cortex is up to as well, right? Somebody that's working with a sound mixing board, right? They might add a little bit of this and take down a little bit of this, add a little bit of this right now. That's what your prefrontal cortex is up to, right? Is it's kind of constantly monitoring the overall flow of everything and making sure you have the right amounts, right? So that what comes out is hopefully the behavior that you decided you want to have come out. So your prefrontal cortex is receiving information from just about everything, all of your different sensory areas, all of your motor areas, a lot of that subcortical stuff, again, including stuff like the amygdala. And what it's doing is it's combining it all together along with some of your other abilities to say, okay, what do I want to do? What's my goal? You know, what steps do I want to take to get there? And am I ready to start doing those steps? And it helps you to decide if you're doing it. And it helps you to check in and go, okay, is this working, or do I need to update my goal? Do I need to update my execution? So your prefrontal cortex is super, super important. And right, it's really important that you also let it rest sometime, but I'll come back to that later. So as far as expressing emotion goes, because that was the original question that I asked you, right, remember the definition of emotion. It's a relatively brief episode of synchronized responses. So those are those bodily responses, including things like facial expressions and your evaluation of it, that indicate the evaluation of an internal or external event. So there's three components to an emotion. You have the autonomic response. That's the stuff that's going to happen automatically whether you like it or not. Right? You're going to have that increased heart rate, for example. That's because of the hypothalamus and those structures send in messages to the endocrine system saying, hey, get the body ready. Now, typically we think of that in a scary situation. That can actually happen if you're really happy too, right? You might have that cool adrenaline rush if you're really happy too. You also have cognitions about it, or things that you think about the experience. Hey, this was really fun, or whoa, that was really scary. That involves the cerebral cortex. And then you also have the amygdala, the subjective parts, the feelings part. And this is where the amygdala comes in, and then again, parts of the frontal lobe. Right? How do I actually feel about what's happening? So you have the response, right? You have the cognitions, and you have the subjective feelings. Now, I want you to write something down right now. If you're listening to my lecture, you're going to get a cheat here. Right? We said that feelings or emotions could also be called your affect. So I want you to write affect, A-F-F-E-C-T here, affect. Okay? And next to autonomic responses, all right, I want you to write out equals behaviors. Right? And what I mean by behaviors is, again, the increased heart rate, dilated pupils, sweating, stuff like that. Because here's how I like to remember the three components of an emotion. I like to remember that it's got A, B, C's. It's got the A's, which are the subjective feelings or the affect. It's got the B's, which are the autonomic behaviors or responses, which is like the heart rate. And then it's got the C's, which are the cognitions. Again, that's how I remember it. All right. So what are you feeling right now? Well, what happens to you when you watch a horror movie? Right? Most people say they get scared. Their heart probably beats. Right? Sometimes your hairs even stand on end. What happens when you find somebody that's super attractive and they start talking to you? Probably the same thing, right? Your heart beats really fast. You get really nervous. What happens when you work out at the gym? Right? Well, your heart beats really fast. You probably get sweaty. So in each of these three cases, I'm getting a lot of the same kind of experience. I'm getting a lot of that same behavioral autonomic response. So really what's interesting about emotion is the actual arousal that you get. And what gives you that is really these other two parts. What you think about it, and then the emotion that you assign to it, or the affect that you assign to it. And that's what the last little bit of this lecture is going to be about, is some of the emotional theories. One of them is called the James Lange theory of emotion, or view of emotion. This is one of the older ones. It was named for two different individuals that came up with this idea. And this idea basically states this, is that you get the physiological changes first. You get those autonomic behavioral things first. You get the blood pressure increase. You get the heart racing. You might get sweaty. You might get shaky. You get that first. And then what happens is that your brain interprets it as an emotion. Your brain sort of looks around at what else is going on, and your brain interprets it as an emotion. For example, let's go back to the three examples that we had. You're having that physical response, right? Your brain looks around, sees the horror movie, and goes, oh, I'm scared. Okay, you're having that response, you look around and you go, oh, I'm attracted to that person. Right? You have that same response and you look around and you go, oh, I'm not really feeling anything. I'm just working out. So again, you don't always have to have an emotion. Sometimes your brain can decide, oh, it really wasn't an emotion at all. This is just how I feel when I work out. So again, the James Lange view of emotion says that first you're going to have the physiology, and then what your brain is going to do is interpret all that stuff that's happening and basically give it an emotion, label it as an emotion. That's where your amygdala comes in, right? It helps influences of conscious awareness of the consequences of the events and objects and connections with the prefrontal cortex. So again, with those three situations, that's what I'm saying. You looked around, you figured out what else was going on. So you raised your conscious awareness of what was happening, what events are happening here, what objects are happening, what's going on. That's that prefrontal cortex going, all right, what's going on here? What does this make sense of? What's going on? All right. What we know is that if you had amygdala damage, it would decrease your fear response. So you wouldn't be as afraid if you were watching that horror movie. You wouldn't necessarily be able to discriminate sexual behaviors, right? And people, for some reason, also have a tendency to examine objects by their mouth when they have amygdala damage, and we're not exactly sure what that's about. What happens if you damage your prefrontal cortex as far as how it affects your emotional behavior? Well, we know that it actually has severe effects, particularly on social and emotional behaviors. And that makes sense because that's what that prefrontal cortex should have been doing, is scanning the situation and saying, is this a scary situation? Is this a happy situation? Is this a neutral situation? And that part gets lost because your frontal lobe just really can't do that anymore. It's not there and it's not working. So people with frontal lobe damage have an inability to experience and express their own emotions and to recognize the emotional expression of other people. They tend to lose their ability to have really initiative or drive to follow and do anything. They don't really tend to set goals well. They definitely don't tend to follow them. They don't really have the ability to plan and organize. They have poor decision making. We've seen this happen a lot in football players that have experienced traumatic brain injury. Now, they don't just have specific prefrontal injury. They tend to have what we call chronic, oh my gosh, the word just left me, something encephalopathy. I'll get there in just a second. But anyway, their whole brain actually gets damaged from the repeated injuries to the head by playing football. All right, but one of the regions that does get damaged is the frontal lobe. And again, some football players have said, yeah, they feel themselves having some trouble with this, especially after they've left the NFL. They don't have the rigid structure that they used to have that sort of took away their need to do things like make decisions, plan out their day, organize their finances, things like that. But what I actually want to show you really quickly is another example, one of the very first examples of us learning about how important the prefrontal cortex was, not just for emotional behavior, although that was important too, but for some of this other stuff about planning, decision making, and things like that. I'm going to talk to you a little bit about a case study about a man named Phineas Gage. Now, I'm going to show you a video. It's a reenactment, but I'm going to tell you right now, slight trigger warning. It is a little bit grotesque. It is a little bit gross. They're going to show what happened to Phineas Gage. So what did actually happen to him is he worked for a railroad company. He was a foreman. Before his injury, he was really, really good. He was really smart. He was really polite and kind. Everybody loved him. He was really good at organizing his crew, making a plan for the day, always on time to work, those sorts of things. In other words, he had really good, healthy, strong, functioning prefrontal cortex. And then one day at work, as they were tamping down the explosives to eventually be able to lay down a new set of railroad track, the explosives detonated too soon, sending a metal tamping iron up through his face, through his cheek, through his eye, through his brain, out the top of his head, and the man lived. And not only did he live, he survived, but afterwards basically had, as you would imagine, all of the symptoms that would accompany somebody that had prefrontal cortex damage. So this is one of the first cases where doctors were like, whoa, hold on. That part of the brain must really have been important for doing some stuff. And again, this happened a while back. Now, what they're showing you here actually is a procedure that used to be done quite a bit that luckily has gone out of favor, which is called a frontal lobotomy. Again, if you're interested at all in that, you can look up some of the details, but it is even more horrid than what I'm about to show you about Phineas Gage. So I'm going to show you just a little bit of a clip of a reenactment talking about Phineas Gage, and then I will return.
In the grand scheme of things, there aren't many ordinary people who have names remembered by history, unless, that is, something extraordinary happens to them. The extraordinary certainly happened to Phineas Gage on September 13, 1848. Unfortunately for Gage, that extraordinary thing was pretty gruesome. Here's why Phineas Gage is still fascinating, even today. What happened? 25-year-old construction foreman Phineas Gage was helping cut a new railway bed through Cavendish, Vermont, and was using a tamping iron to pack explosives into a hole. And then, this happened. The explosives detonated early and sent the 4-foot, 13-pound tamping iron through his left cheek, into his brain, and out his skull. Making things worse, according to legend, he might not have even lost consciousness. Historical documents say that he was driven into town where he sat on a porch chair and chatted to passers-by as he waited for Dr. John Harlow. After a few days, he developed a brain infection that left him even closer to the Grim Reaper's door. But the Reaper had apparently been impressed enough with what he'd already survived to give him a pass. He recovered, lost use of his left eye, and went home 2 months later. Everyone who knew him before and after the accident agreed he had changed. And when he died in 1860 after suffering a series of seizures, he remained a part of historical and medical infamy. Pioneering neurology. Gage is one of the earliest documented cases of traumatic brain injury, and his accident couldn't have come at a better time for the science of neurology. When Dr. Harlow first documented Gage's story in the Boston Medical and Surgical Journal in 1848, no one believed it. It wasn't until 1850 when Harvard professor Henry J. Bigelow wrote a piece on him being a fully functional human post-accident that people started to notice this medical miracle. Bigelow's follow-up report in 1868 focused on the mental manifestations of the accident, saying he had become fitful, irreverent, indulging at times in the grossest profanity, and manifesting but little deference for his fellows. In short, the guy who got a giant metal spike through his head allegedly became a jerk. Neurologists at the time insisted that we needed to look inside the brain to unlock the secrets of what made us human, and Gage was the first documented case that provided evidence for this. So we should probably be thanking Gage for his unwitting scientific contributions.
Okay, welcome back. So hopefully that wasn't too horrifying for you, or if it was, I hope you just skipped it. But nonetheless, again, what we learned from this unfortunate case of Phineas Gage is, again, just how important the prefrontal cortex was, not just for controlling a person's ability to do things like make decisions, plan, and organize, but also for their ability to express emotional, especially appropriate emotional behavior. The last two slides that I'm going to do before we are done with this lecture sort of ties into another major category of things that we study in psychology, which would be emotional disorders. The first one that I want to talk to you a little bit about is major depression. Major depression is considered a mood disorder. It's characterized by prolonged feelings of worthlessness and guilt, disrupted eating and sleeping habits. So sometimes people will eat too much or not enough. Sometimes people will sleep too much or not enough, a general slowing of behavior, frequent thoughts of suicide. There does seem to be a genetic component to major depression. There does seem to be some sort of what we call epigenetic changes as well. In other words, what we know is that early life stressors, which are now being called adverse childhood experiences or ACEs, seem to produce epigenetic changes in the way that the prefrontal cortex develops, and it also seems to change the way that the amygdala starts to function. And so we think that this is why it sets somebody up having these early childhood negative experiences for ultimately being more likely to experience major depression later on. And again, this fits right in with what we were saying. If your amygdala and your prefrontal cortex aren't functioning the way they should be functioning, it is very likely that you're not going to be able to regulate your emotional expression as well as you would otherwise. The second emotional disorder that has some implications here for what we've been talking about are anxiety disorders, which are similar to mood disorders, but slightly different. And there are three different kinds of anxiety disorders that I'm going to talk about here. The first one is just generalized anxiety disorders. This is just when you have a persistent high level of anxiety that's accompanied by maladaptive behaviors to reduce that anxiety. So this could just be something like you're just chronically feeling stressed. You might do something else that's negative to reduce the stress, like use some sort of substance, maybe alcohol or something like that. But again, the point is you can't seem to regulate your own level of anxiety, which is sort of an extreme form of emotional expression. And as you might imagine, if you've never experienced that, that feels absolutely awful. And it's definitely not a generally pleasant experience of emotion for people. And so they tend to find ways to deal with that emotional expression or to stop that emotional expression. Another kind of an anxiety disorder is a phobia. And this is when you are experiencing that anxiety, but it's at a clearly defined object or situation. So a fear of heights, a fear of certain objects, like arachnophobia would be a fear of spiders. And again, this isn't just me not liking spiders. Phobias are even more extreme. And then the third is a panic disorder. And this is where you get not only that sense of anxiety and all of that other stuff that we said was already not a pleasant thing to experience, but then you also have recurrent attacks of intense terror that can come on without warning and without apparent relation to any sort of actual external circumstances. So it's not like you see something scary and you feel panicked, or something bad happens and you feel panicked. It's a random moment in the middle of my random day, and nothing has happened to me today, good or bad. And then all of a sudden I'm having this panic attack. And so, as you can imagine with these emotional disorders, again, there's something that has gone awry between the communication between the amygdala and the prefrontal cortex and probably some other brain areas. And this is kind of where we are in sort of the neuroscience field, which is, blending with some of the medical fields, is looking at, first of all, what exactly has gone wrong here? Why aren't these brain regions communicating the way that we know that they're supposed to communicate? That's sort of the first part. And then the second part is what can we do about it? Can we fix the communication itself? That's one way we can answer that question. And the other way we can answer it is there are other ways that we can get this person to stop having these symptoms and these experiences. And actually what's really interesting is that there is some new research out there that says, yeah, we actually can. So I'm going to end this lecture with somebody that's talking about some of this newest research, about some of the new things that they have been doing to get rid of fears. And I just think it's really cool, really fascinating research. It's not too long. It's only a couple minutes, and then we will be done. So again, watch that, and then that will conclude our second lecture here.
In everyday life, we have all sorts of fears, and my personal experience with fear is parachuting. I did it several times, and I discovered it's very scary. But then I got interested in how you overcome fear. And my line of experiments deals exactly with that, how we overcome fear, how we change fear. And the particular experiment we just published now in Nature is about preventing fear altogether, preventing it from returning.
In this experiment, we studied a very simple type of fear learning where we present you with a neutral stimulus like a yellow square, and we pair it with a shock. After a few pairings, your body elicits a fear response. We measure this by measuring the skin conductance response.
Okay, that was enough. And you can see the response on the computer. That's a very strong response.
It's really just the electrical conductivity of your sweat glands, and that's just part of the natural arousal response you would have with fear. What we can do, though, we can get rid of that fear now just by presenting the yellow square over and over and over again and have nothing bad happen. Eventually you're going to learn that the yellow square doesn't predict shock, and I'm not going to see this fear response in your body. So this is called extinction. And it works pretty well. It's the basis for treatments for phobias. The problem with that type of learning is that what we've done, and we know this from a lot of behavioral studies in humans and other species, is we've created two memories. Yellow square predicts shock, and a second one, yellow square does not predict shock. And the problem is over time, those two memories compete for expression. And this is one of the big challenges in treating anxiety disorders. We can get people in the clinic to not be so afraid of things, but now you get them out in a stressful situation and all of a sudden those fears come back. It's the fact that we have two memory representations that are competing that leads this to happen.
So what we found in our experiment is that the way to get around the problem of fear coming back is to remind the fear memory before we do extinction training. So to remind the fearful memory, we just present the yellow square again. This brings back the fear. Then we wait a little bit, and then we start with extinction training, which is presenting the yellow square again and again. This manipulation keeps the memory extinguished. It prevents the fear memory from returning. So the reason why it works is because we take advantage of a phase of memory called reconsolidation. And this is a process that happens naturally whenever we remember something. A nice way to think about it is like a file on your computer. You have a file a document you wrote and it's stored. Then you open it, you update. You put in new information, then you save it and store it again. So now it's stored in a new form. It doesn't create a new file in addition to the old file. You have just one file, but now it's updated. So what we do is reactivate the memory. It goes into this phase called reconsolidation, which is basically the restorage of the memory. If we do extinction training at that time, it doesn't form a new memory. The information acquired through extinction is merged into the original memory and it changes its original properties. So now we have one memory, but stored in a different form.
And now what we would expect is the case in that situation is when we wait a day, the fear doesn't come back. When we stress you, the fear doesn't come back. And that's exactly what we found. The big difference between this and what you see in the Eternal Sunshine of the Spotless Mind is here we're targeting a very specific fear memory, not your ability to recollect information. So in that movie, Jim Carrey wanted to completely forget Kate Winslet altogether. Here, because this specific type of fear memory, which is represented in your body's response to a fearful event, we're eliminating the memory of that. You will still be able to tell me what happened. And you will still, have all of that information available because that's another kind of memory we didn't target.
And that's a good thing because if you supposedly erase memories, you don't want to create blanks in your life that the whole parts are missing. If you still remember the content, you have continuity in your life. You just change your emotional response. So the intrusive emotional fear doesn't interrupt your everyday life whenever you remember. You can remember, but it's not stressful anymore.
So, at this point, how this works in the clinic is going to be all speculation. But what this data suggests might happen in the future is if you come into the clinic with a fear-related disorder like a phobia or PTSD, if we can understand how these memories are restored when they're retrieved, much as we did in this study, we then may be able to time our therapeutic interventions in such a way where we aren't creating new learning that's overriding those earlier memories, but actually rewriting them in a sense. If we can time that correctly so we can target these mechanisms, perhaps we'd have a more effective, long-lasting outcome.